Do this. Okay, good. All right. Now, let's go to there we go. All right. Where's Acrobat? Right here. Okay. So we're going to be talking the sort of last bit about the 1850 to 1900 about electromagnetism, as everybody always assumed that Newton had gotten everything right. They found some things that didn't seem to make sense. So we're going to talk about that. So we're going to talk about various people who worked on this and are mostly the most important people. Hendrik Lorentz for the mathematics and Micaelson and Morley for their experiment. So we're going to be talking about the ether, the trials and tribulations of the ether. Albert Micaelson on the right upper, he was just an amazing experimentalist.
Bob, nothing changed. I just got your introductory screen.
Oh, that's weird. For some reason, it says it's paused. Okay. How do I? Have we got it now?
No.
The heck? I keep clicking resume share and nothing changes. So I'm going to stop the share and then I'm going to share again. That's really very annoying. So do you see the contents now?
Yes.
Yeah, yes.
Okay. Sorry, I have no idea why. I kept clicking the button that says to resume share and it did nothing. So
Are you still recording?
I hope so. I didn't hear it stop. So anyway, okay. As I said, we're going to be talking about.
Excuse me, before I forget this, but I just encountered a thing where my USB connector has gotten some lint in it, and it's not charging. So I don't know if a USB connector may be an issue for you, but this was the first time I ran into it, and so that's something I didn't expect. So USB connectors can get lint in them.
Yeah. Well, I do everything on Ethernet. So anyway, okay. So we're going to talk, as I said, about the two main people who are, or three people, I should say, Micaelson, Morley, and Lorentz. Micaelson and Morley were the experimentalists, and Lorentz was the mathematician or mathematical physicist. Come on. Okay. You can see waves in the ether?
Yes.
Okay, great. At least it's working now. All right. So this is an actual picture of the interferometer that Micaelson created, Micaelson and Morley. And it was, you see the huge granite block that he had, and they had these various mirrors, and in the upper, in the corner here, they had the measurement. Anyway,
What's the pool of mercury for?
to make it not, you might have a truck driving by, and there'd be some vibrations, and so this was basically a way of damping all the other vibrations that were going on around them. Okay, Micaelson. Well, I loved his quote. If a poet could at the same time be a physicist, he might convey to others the pleasure, the satisfaction, the reverence which the subject inspires. I thought that was great. Hadn't heard it before until I was setting up these lectures, and I just loved it. Anyway, they did their experiment, and of course, it didn't work, which really surprised them. And Morley said, "It appears from all that precedes, reasonably certain, that if there is any relative motion between the Earth and the luminiferous ether, it must be small." And later, after 1905, and Einstein's special relativity made the ether superfluous, he said, if the Micaelson-Morley experiment had not brought us into this serious embarrassment, no one would have regarded the relativity theory as a halfway redemption. So anyway, interesting people.
So, Bob,
Yeah.
you might explain what they were trying to measure.
Oh, we're going to talk about that.
Okay.
So in Faraday and in Maxwell's mathematization of Faraday's field, as we talked about previously, he found these transverse undulations, waves. And he concluded, because he had two measurements on epsilon and mu, and you looked at the wave equation here, you got this product of those two. The zero means it's in the vacuum. And in a wave equation, this is 1 over the speed of the velocity of the waves as they move in time. So he concluded from the numbers that these two came up with, and you multiply them, turn out to be the same as 1 over c squared. So he said, it moves as sines and cosines at the speed of light. So electromagnetic radiation is nothing more than light, or light is nothing more than electromagnetic radiation. So that's the proper way to say it. Anyway, so these are the E and B wave equations that Maxwell came up with. And any Cambridge Wrangler, and he was the second Wrangler in his year, knew the general form of a wave equation, which I wrote it at the top here. And as I said, 1 over v squared is the speed of the traveling wave. And the f of x and t is then two constants because it's a second order equation, so you need two initial conditions. And you have a sine of kx plus omega t and a cosine of kx of omega t. So that means that you get this undulation, and the distance between peaks is the wavelength in space, and it's the period in time. So these are all things that he knew, and like I said, when he found the measurements for mu 0 and epsilon 0, he knew that they were the same as 1 over c squared, the speed of light, which had also been measured. So, as I said, that meant that, oh, yeah, I'm just repeating myself, sorry. So he got his experimental measurements and found that they were essentially the same as the speed of light, and light was nothing more than waves in E and B.
Bob, I have a question. Is how did they get the values of epsilon and mu?
Well, these are, you can do it with several things that Faraday discovered. They are various kinds of strains in the field, and Faraday had created many of the experiments to do that, and so he had done some of the experiments initially, but they improved them over time. And by, I think, the 1880s or so, that was when the measurements were so clear that it had to be the same as the speed of light. It also improved the measurements on the speed of light at the same time. So anyway, Hendrik Lorentz. Lorentz was a Dutch mathematical physicist, and like everybody else, he assumed that if you're going to use mathematical translations, what was going to happen? There were a couple of things. First of all, if you have waves in something. You have waves in water. You have waves in air. So there must be something that's being waved. So they created this thing called the luminiferous ether, and that was the fluid or whatever it was that was waving in Maxwell's equations. So what happens if you're moving against a ship? You'll find that, in one direction it's different from the other direction. So, of course, you have to go back to Galileo and do the coordinate transformations, which Newton accepted and used for any coordinate transitions. So if you're moving through a material of speed v, then x prime will be x minus vt, and all the others will be identical. If you do that with Maxwell's equations, you find that that means a couple of extra terms turn out into the equation. It's no longer a simple solution of sines and cosines, but it's got all these other terms in it, and you'll get other things non-sinusoidal. Unfortunately, as the screen says, that's not what we measure. When we measure everything, we always get sines and cosines. So the idea eventually was that, if you look at, if everything is the ether, everything is in the ether throughout the universe, then when the Earth is going around on one side of the sun, it'll be going in one direction against it, and in the other side, it'll be going in the opposite direction. So there should be this effect, but you never saw that. So he got this electrodynamics of moving bodies paper, and in 1895, he introduced a new time variable. He called it local time. And then if the equation for the change of time, which was a function of the original time, velocity, and x, if you use that time, then you could save Maxwell's wave equations, and you'd always have sines and cosines. Now, Lorentz never thought that this meant anything physically. He thought it was simply a way to get the results that he was looking for, and the t in the t prime was the time that was going on in the ether. The ether was something that was the rest frame for everything in the universe. Any questions?
Yeah, I have a question. I worked in some stuff like this. I even had a 8,000-pound granite table. The principle was it was heavy and it would float. But it seems to me that what you're ignoring is the Earth rotates on its axis, and that would be the main rotation to be considered. Did you say like different times of the year?
They did it different times of the day. They did it different times of the year. But we're getting there. You're getting ahead of ourselves. That was Micaelson and Morley. Lorentz just was trying to save the sines and cosines that came out of the wave equation, because they never saw anything other than sines and cosines in the measurements.
Okay, I'm just saying the beams in these experiments would always have the rotation of the Earth.
Right. No, they, like I said, they did it at different times of the day. They did it at different times of the week, different times of the year. So they did it many, many times, and at, like I say, but we're getting ahead of ourselves. That's the next section.
Okay.
Any other questions? Okay, we're going to talk about the Micaelson-Morley experiment. So, Lorenz knew that the light propagated in the ether because there had to be something that was waving. And the national question was asked was, how could one detect the Earth's motion through the ether based on the behavior of light on Earth? And the effect would be like a bicyclist feeling a headwind when moving through the atmosphere. And beginning in the early 1880s, Micaelson and Morley sought to design, to measure such an effect, to do an experiment that would actually measure that effect. And he designed and built a new type of device called an interferometer, and to try and measure the effects of the Earth's motion through the ether on the propagation of light. Micaelson's work was the first work done by physicists in the US that people in Europe actually considered worth paying attention to. He became the first US-based physicist to win the Nobel Prize in 1907. How does it work? Well, let's consider a swimmer, no W in that, sorry, typo, in a river. Assuming that the swimmer can swim faster than the river flows, otherwise you're going to go downhill no matter what, downriver no matter what. If you can move faster than the river flows, you can choose an appropriate angle at which you'll swim, and then you'll be able to go side to side for some time. On the other hand, if the swimmer goes up and down the river, then going against the flow, it'll take much longer than the downstream swim. And the thing we're going to do is compute the difference between those two. So the downstream will be short, the upstream will be longer. The sum of the two will probably, or we'll see that, will be different in the two different ways of doing it, across and up and down. So here we have a stream, a river, and it's got a velocity going down here, and you have a distance between them of L equals 10. So you can go from A to C and C to A, and you can use the same length, L equals 10, and go from A to B and down from B to A. So you have to figure out the angle at which, the swimmer can swim at 7 as opposed to the -2. So you have to use some of that against the flowing river in order to keep going along this, keep going straight. And similarly, you have to go it that way, going back. Okay, so you can calculate it for this velocity, what the angle is you have to be at, and doesn't matter. Just trust me that those numbers are accurate. Okay, so you're swimming along this angle, and you're going at that angle. So you're losing some of your speed. You're doing less than your 7 as you go across and when you go back. So you keep swimming at that angle and eventually get here. Now, if you do the same going the opposite direction. Okay. So when you're going vertically up, you're 7 minus 2, and therefore your 7 minus 2 is 5. 10 divided by 5 is 2 going up. Coming down, it's still 10, but you're 7 plus 2, so 7 divided by 9. It only takes 1.11 coming down. Okay. So Micaelson's insight was to discover that interference of light is a very sensitive test. As I said before, you can have a same distance going up and down. You'll have two different, oh, I should have gone up here, sorry. So this is 1.1, whoops, sorry. 1.1 and 2, 3.11, and the previous one, come on, was 1.49, so twice that, almost 3. So they're different, swimming this way and back and swimming that way and back. That was the point. Okay, so you can do it all just in algebra, of course. So the AB and BA, this is going up and down against the river and with it. And that'll be 2L over C, 1 minus 1. Sorry, I'm having something in my throat, and I hope it's understandable. Sorry. Anyway, so on the other direction, you've got that 2L over C, 1 over the square root of 1 minus V squared over C squared. So the difference between the two times is going to be a different amount because one is the square root and the other is not. Sorry. Okay. So the function here on the left, gamma, is known as the Lorentz factor, and it's the 1 over square root of 1 minus V squared over C squared. So who wins the race? Well, TABA is 2L over 1 minus V squared, and TACA is 2L over 1 over the square root. So when you take a look at the difference between those two, you find out that there is a small difference where ABA will be faster than ACA, and it's a V squared over C squared amount. So the order of error is V over C to the 4th. So the effect is very small, which was why when Micaelson discovered the interferometer, he was able to measure these very small effects accurately. Okay, how did the interferometer work? Well, you got a source. Here we're talking about light. You run it through a beam splitter, and one way it goes up and down to the mirrors, And when it goes through the beam splitter the second time, it's going to go to the sample. So you interfere between the two beams in the directions, and the effect can be measured because it's very, very accurate. You'll see an effect here. This on the left, this is the shift in the height and lower end. The detector will see a shift in these lines. Okay. So if the light waves travel path 1 took a longer time than through path 2, the waves will arrive at the screen out of phase, and the crests from one wave will no longer line up with the crests from the other. That's the interference effect. And in 1887, with L equals 11 meters, and the entire apparatus floating in a vat of mercury to dampen vibrations, and mercury is quite dangerous, so don't try this at home. I can tell you for sure, it's a lot of fun. I got a hold of some mercury and played with it when I was a kid, but not a good idea. Anyway, so this is the way his system worked. And whoops, that's the wrong picture. Sorry. Crap. If you take a look at the picture and grab the wrong one, sorry, you would expect a sinusoidal effect over time when you measured it over the day, over the week, over the year. You'd see that kind of effect. When they saw the effect, there was a very slight up and down, not anywhere near the amount that was expected. So, sorry, I have a video. Let me see if maybe I can go. Anybody want to pause the share and go see what the picture looks like? I can find it. Pause. Okay, back to the meeting. Let's go find the, hey. God damn it. This system just drives me crazy. All right. So, where are we? We're here, there. Picks. Okay. Which is the one that has Micaelson-Morley experiment? No. Experiment? No. Where is it here? There it is. No, that's not it either. Well, looks like the reason I picked a different one was because I destroyed the old one. Sorry. Okay, let me go back to the meeting. Resume. Hey, I'm screen sharing. How about that? Wouldn't do that last time. So you can see the slides again? Yes or no? Somebody
No, I can't.
can't. Stop the share. Somebody. This drives me crazy. Their stupid system.
Is this a problem with Zoom or something else?
It's a problem with Zoom. Zoom keeps doing screwy stuff and they keep changing it. And half the time it doesn't work. Just drives me completely crazy.
I wonder if there's something that works better than Zoom.
I wish there were.
Has anyone tried Jitsi?
No, I've never heard of it. So,
Well, a lot of people use it, and it's rated pretty highly.
okay. We'll talk about it later and I'll go take a look at it. But in the meantime, I'd like to get back to the meeting. It just won't go back to the meeting. It is, oh, okay, good. Come on. Take down. It's on the bottom, covered with the dock. Finally, share. Where's my slides? Where's my slides? Okay. Nobody sees this, I assume. Do you see the slides?
Oh, we just see
No.
Yeah,
the
okay.
folks that are watching.
Now do you see it?
Yes, we see something different.
Okay.
Stars and things like that.
Yeah. As I said, the picture, if you go to the actual stuff that was the article that was written, you'll find a effect size which is about 40 times larger than what they measured. So the results were only consistent with the change in time being zero, rather than the effect on order of 10 to the minus 8, which they were easily able to measure. So anyway.
I'm seeing something that looks like it's screenshot or something like that.
Huh? All right, let me stop the share. Share that desktop. Is this? No. Okay. That's. Do you see it now?
Yes.
Now it's good.
Okay.
Showing up.
All right. So the sensitivity that they could measure to was about 10 to the minus eighth. And yet the result they got was a null result. So the quote from the paper is, "It seems fair to conclude from the figure that if there is any displacement due to the relative motion of the Earth and the luminiferous ether, this cannot be much greater than about 1/100 of the distance between the fringes." So the actual displacement was certainly less than a 20th part of the expected value, and probably less than a 40th part. So that was their final conclusions in the paper. So it's available, and the experiment is on the relative motion of the Earth and the luminiferous ether by Micaelson and Morley. If you're interested, I can send you a copy of the paper.
Why did Micaelson think the experiment was a failure?
Well, because he believed in the ether.
Even after Einstein?
Oh, yeah. Yeah. No, when he died, he still believed Newton was right. And the ether, there had to be something that you were waving in. I mean, the idea that something could wave with nothing to wave, no material going up and down, just didn't make any sense to him. As far as he was concerned, that was just, magic. And he would not believe in magic. So any questions? All right. So Lorentz also was able to show an effect that is known as the Lorentz contraction. Lorentz followed Micaelson's work closely, and following Micaelson's work, he decided that physicists had neglected a physical contraction of the apparatus along its direction of motion through the ether. So if the molecules in the arm of the interferometer, and here's a picture of, say, a beach ball going through water, it might compress it in one direction and not the others. So if the molecules in the arm of the interferometer would be squeezed due to their motion through the luminiferous ether, then that would shorten the length of the arm, and that would directly affect the ether wind length contraction. So the swimmer would have less distance to cover for her lap, and the 2 lap times would turn out to be equal. So he came up with this effect. And so if the distance was shortened by 1/gamma, then the 2 times would be equal, and the race would be a tie. And no wonder Micaelson and Morley measured no shift in the interference fringes. So he came up with a way to think about it that might save the ether. He developed these transformations that he had come before the local time and the length contraction, and derived a new set of transformations from bodies moving with respect to the ether, replacing the Galilean transformations. So the Galilean transformation is just x plus or minus the velocity times t, but he's got this gamma factor, which when it's small relative to the velocity of light is essentially 1, but when it gets close to the speed of light, then it gets quite large. So the shrink, the effect will be quite large on the distance, and the time, which becomes a function of x. The reason it was done that way was to make the wave equations stay the wave equations. And so if you take a look at what 1 over the square root of 1 minus v squared is when you do the binomial approximation, then you get 1 plus v squared over c squared. So, that'll be an order of v over c to the 4th. And if v is much less than c, you're just not going to see that effect. So, and if it is essentially 1, then the x prime becomes the same as the Galilean transformation, because the gamma is essentially 1. And because vx over c squared, when c is very large, this amount is going to be essentially negligible if v is much less than c, and therefore t becomes t prime. So his transformation saved the Galilean transformations when velocity was very small. Everybody follow that?
Yeah.
Okay. Pardon? Question? Okay. When he applied his transformations to the wave equation that Maxwell came up with, lo and behold, the x prime and t prime turn out to be exactly what they were from t and x. You get a wave equation. So you should always, even when you're moving the Earth, light should travel at the speed c, and E and B fields should oscillate like sines and cosines. So Maxwell's wave equation is saved. So what did we have? Okay. Lorentz had addressed 2 puzzles about electrodynamics of moving bodies. By the mathematical trick of local time and the experimental null results from Micaelson-Morley using his version of transformations, which looked like Galilean transformations as long as the velocity was small, then since the ether was a physical medium, elastic medium, it would exert a force on the objects moving through it, and there'd be a physical contraction of the objects along their direction. And the general strategy he started to think about was think about the dynamics, the study of forces, the fact that the molecules might be compressed, and then use that effect to account for the motion of the objects. So that was what he came up with. And most people weren't sure about it, but they sure liked it because it saved Newtonian effects. And at the same time, there were still people in Europe like Coulomb who still thought that the whole idea of it being a finite speed was crazy. It was obviously going to be non-local in a straight line like Newton's gravity. So there was all kinds of people still trying to hang on to Newton's stuff. Unfortunately, or fortunately for us, a little unknown patent clerk in Switzerland had some different ideas. And we'll probably talk about that next. Well, not next. Next, we'll do an Ask Me Anything question when we meet with at Kathleen's house. And then the one time I do after that will be when we'll start to actually get into the 20th century, talk about Planck and Einstein. Okay, any last questions? Okay, that's all the material I got today. Sorry. Let me go back to the meeting, stop the share. And if you got any questions, I'll be happy to answer them.
Well, that was very helpful in understanding the credibility or plausibility of Lorentz's save. I can't wait until we hear why Einstein wasn't happy.
Well, he was unhappy for a completely different reason. Einstein looked, again, even Maxwell thought Newton's ideas were correct. And in that idea, when you suppose you have a magnet and a coil of wire. Now you take the magnet and you move it in and out of the wire. You get a current out of it. The other thing you can do is take the coil and move it up and down over the magnet, and you get the same current. But the picture from Maxwell's equations using the Newtonian ideas are completely different. You get a completely different picture of how that current appears in the two same, one is relative to the other. And that's what Einstein, that's why it was called relativity, because he wanted anything you could do this way, you could do this way, and it should work exactly the same. And you shouldn't have two different pictures for how the current occurs. So that was what he was doing. He was trying to look at the two different pictures you had for magnetic versus electric field solutions for the same motion, same relative motion. So that was what he was worried about. Turned out that it also gave the same Lorentz transformations. And once Noether showed that invariance was a function of the transformations, the relativity became obvious at that point. So that was what Einstein was doing. He was worried about the fact that the two pictures were completely different for the electric field and the magnetic field, and he felt they should be the same. And in point of fact, when you use special relativity as the basis, then it depends upon who's looking. For one person, it'll be all electric. For another person, it'll be all magnetic, and others will be a combination of the two. So it all depends upon who's looking in Einstein's picture. So that was how he saved the electromagnetic equations, not by trying to be Newton, but trying to be, have it be the same picture no matter who was looking.
But wasn't Lorentz right in a sense that objects do shrink close to the speed of light in the direction of motion?
Yes, he was right about that, but he thought the time was completely fictitious, just a mathematical trick. And in time dilation, you can measure it. It's real. So, when you have stuff coming down at high speed into the atmosphere, particles, they'll bounce off something and then come down to the Earth. And we've measured their decay time in the laboratory many, many times, and we know the average amount of time. But it's moving at high speed when it hits the air and comes down to the Earth. And because of that high speed, it lengthens the amount of time it takes to get to the Earth. If it were the amount we measured in the laboratory, it'd go a few meters, but instead it goes all the way to the surface of the Earth after being hit up, hundreds of kilometers, more than hundreds of thousands of kilometers up. So anyway, we've measured those effects as well. So time dilation is not a mathematical trick. It's real.
Are you familiar with the Pollitt wave type work that Einstein did after he did that for, they say, much longer than he worked on relativity, and I think he never really published in that area. And are you familiar with that work?
Yeah, unfortunately, that was Bohm's rediscovery of de Broglie's 27 idea. Unfortunately, we've just done an experiment because we've gotten time, so we've been able to measure time down to about 10 to the minus 21st seconds, 10 to the minus 21st seconds. And using that, we've finally been able to actually measure the time that you know, quantum particles can go through solid objects and tunneling, quantum tunneling. So we've finally been able to measure quantum tunneling. And in the latest experiments, it works in the opposite way that the pilot wave quantum mechanics says. And I love pilot. That was my favorite form of quantum mechanics until I read that paper. It was Bell's favorite. So I don't know what we can say except, sorry, it doesn't work experimentally. The measurements go in the opposite direction that the pilot wave says they would. So that's...
Yeah, well, I think you're talking about a specific pilot wave theory, and Einstein worked on, like, I'm going to get some ideas, and he sort of said something like that had to be going on, and I don't know that he elevated to where he could calculate or things like that, but he was very disturbed by that for years, and worked on the wave particle duality side, and he was unhappy with that very much. And
well, he was basically unhappy because quantum mechanics is non-local, and he wanted locality. That was what relativity was all about, locality. And he was never able to create anything that was local, and eventually using the assumptions that Bell made, basically that experiments can be independent of each other, then you could have, you would show that quantum mechanics was non-local. And pilot wave is non-local in your face. I mean, it's non-local everywhere. So that was the reason he never, Einstein wanted locality, not non-locality. So that's why he never followed up very much on pilot wave. Even though he was very aware of it, he didn't like anything that was non-local. And like I said, Bell eventually showed that quantum mechanics is non-local. Sorry. And we've done it experimentally and showed that it's non-local. So I like to think, of course, this all happened after Einstein died, so we don't know. But I like to think, he would not object with experiments. And because we've shown that quantum mechanics is non-local, he would finally say, "Oh, I was wrong." It's
but the physics is always completely wrong. So the odds are it's going to be completely wrong again, right? And
of course,
all the interpretations of quantum mechanics, they're all different. And the paper I was circulating around to you guys about a year ago, if you look at it, it's a bunch of people that disagree with one another. When they have or may have perfect math that they can work with their quantum, with their interpretation. But when it comes down to what one of them believes and what the other one does, they're all in disagreement. So, when the top people are all disagreeing, that doesn't look like a very good position. They're all saying what is really happening, we don't understand, and they disagree, right?
Yeah, well, one of the things that, anybody who thinks about quantum mechanics and understands that general relativity works means that all of the computations we do in particle physics are garbage. They use this S matrix. The
Something's
assumption
wrong with the communication.
Yeah, the S matrix makes the assumption that you start from t equals minus infinity and x equals minus infinity. And then it travels through, goes through your laboratory, interacts, and goes off to plus x equals infinity equals. Oh, sorry, I should stop that. Anyway, let me. Where do I stop there?